Greetings, tech enthusiasts. Welcome back to our channel. Today, we're diving deep into the fascinating computing world, specifically parallel computing. Have you ever wondered how supercomputers crunch massive amounts of data or how complex simulations run seamlessly? Well, you're in the right place. In this video, we'll explore the fundamentals of parallel computing, demystifying the technology behind it. So, buckle up and let's embark on this exciting journey together. Let's understand first what is parallel computing. The simultaneous execution of many tasks or processes by utilizing various computing resources, such as multiple processors or computer nodes, to solve a computational problem is referred to as parallel computing. It is a technique for enhancing computation performance and efficiency by splitting a difficult operation into smaller subtasks that may be completed concurrently. Tasks are broken down into smaller components in parallel computing, with each component running simultaneously on a different computer resource. These resources may consist of separate processing cores in a single computer, a network of computers, or specialized high-performance computing platforms. Various methods to enable parallel computing. Different frameworks and programming models have been created to support parallel computing. The design and implementation of parallel algorithms are made easier by these models' abstractions and tools. Programming models that are often utilized include Message Passing Interface, MPI. The Message Passing Interface, MPI, is a popular approach for developing parallel computing systems, particularly in situations with distributed memory. Through message passing, it allows communication as well as collaboration between various processes. CUDA, NVIDIA designed CUDA, a platform for parallel computing and a programming language. It gives programmers the ability to use general-purpose parallel computing to its full potential using NVIDIA GPUs. OpenMP, for shared memory parallel programming, OpenMP is a well-liked approach. It enables programmers to define parallel portions in their code, which are then processed by several threads running on various processors. Types of parallel computing. There are 4 types of parallel computing. First one is bit-level parallelism, the simultaneous execution of operations on multiple bits or binary digits of a data element is referred to as bit-level parallelism in parallel computing. It is a type of parallelism that uses hardware architecture's parallel processing abilities to operate on multiple bits concurrently. Bit-level parallelism is very effective for operations on binary data such as addition, subtraction, multiplication, and logical operations. The execution time may be considerably decreased by executing these actions on several bits at the same time, resulting in enhanced performance. For example, consider the addition of two binary numbers, 1101 and 1010. As part of sequential processing, the addition would be carried out bit by bit, beginning with the least significant bit, LSB, and moving any carry bits to the following bit. The addition can be carried out concurrently for each pair of related bits when bit-level parallelism is used, taking advantage of the capabilities of parallel processing. Faster execution is possible as a result, and performance is enhanced overall. Specialized hardware elements that can operate on several bits at once, such as parallel adders, multipliers, or logic gates, are frequently used to implement bit-level parallelism. Modern processors may also have SIMD, single instruction, multiple data, instructions, or vector processing units, which allow operations on multiple data components, including multiple bits, to be executed in parallel. Second one is instruction-level parallelism, ILP, or instruction-level parallelism, is a parallel computing concept that focuses on running several instructions concurrently on a single processor. Instead of relying on numerous processors or computing resources, it seeks to utilize the natural parallelism present in a program at the instruction level. Instructions are carried out consecutively by traditional processors, one after the other. Nevertheless, many programs contain independent instructions that can be carried out concurrently without interfering with one another's output. To increase performance, instruction-level parallelism seeks to recognize and take advantage of these separate instructions. Instruction-level parallelism can be achieved via a variety of methods. Pipelining. Pipelining divides the process of executing instructions into several steps, each of which may carry out more than one command at once. This enables the execution of many instructions to overlap while they are in different stages of execution. Each step carries out a distinct task, such as fetching, decoding, executing, and writing back instructions. Out-of-order execution. According to the availability of input data and execution resources, the processor dynamically rearranges instructions during out-of-order execution. This enhances the utilization of execution units and decreases idle time by enabling independent instructions to be executed out of the order they were originally coded. Third one is task parallelism. The idea of task parallelism in parallel computing refers to the division of a program or computation into many tasks that can be carried out concurrently. Each task is autonomous and can run on a different processing unit, such as several cores in a multi-core CPU or nodes in a distributed computing system. The division of the work into separate tasks rather than the division of the data is the main focus of task parallelism. When conducted concurrently, the jobs can make use of the parallel processing capabilities available and often operate on various subsets of the input data. This strategy is especially helpful when the tasks are autonomous or just loosely dependent on one another. Task parallelism's primary objective is to maximize the use of available computational resources and enhance the program's or computation's overall performance. In comparison to sequential execution, the execution time can be greatly decreased by running numerous processes concurrently. Task parallelism can be carried out in various ways, few of which are thread-based parallelism. This involves breaking up a single program into several threads of execution. When running simultaneously on various cores or processors, each thread stands for a distinct task. Commonly, shared memory systems employ thread-based parallelism. Task-based parallelism. Tasks are explicitly defined and scheduled for execution in this model. A task scheduler dynamically assigns tasks to available processing resources, taking dependencies and load balance into consideration. Task-based parallelism is a versatile and effective method of expressing parallelism that may be used with other parallel programming paradigms. Process-based parallelism. This method involves splitting the program into many processes, each of which represents a separate task. In a distributed computing system, processes can operate on different compute nodes concurrently. In distributed memory systems, process-based parallelism is often used. Fourth one is superword-level parallelism. Superword-level parallelism is a parallel computing concept that concentrates on utilizing parallelism at the word or vector level to enhance computation performance. Architectures that enable SIMD, single instruction, multiple data, or vector operations are particularly suited for their use. Finding and classifying data activities into vector or array operations is a core concept of superword-level parallelism. The parallelism built within the data may be fully utilized by conducting computations on several data pieces in a single instruction. Superword-level parallelism is particularly beneficial for applications with predictable data access patterns and easily parallelizable calculations. In applications where a lot of data may be handled concurrently, such as scientific simulations, picture and video processing, signal processing, and data analytics. It is frequently employed. Applications of parallel computing. Parallel computing is widely applied in various fields, and a few of its applications are financial modeling and risk analysis. In financial modeling and risk analysis, parallel computing is used to run the complex computations and simulations needed in fields like risk analysis, portfolio optimization, option pricing, and Monte Carlo simulations. In financial applications, parallel algorithms facilitate quicker analysis and decision-making. Data analytics and big data processing. To process and analyze large datasets effectively in the modern era of big data, parallel computing has become crucial. To speed up data processing, machine learning, and data mining, parallel frameworks like Apache Hadoop and Apache Spark distribute data and computations across a cluster of computers. Parallel database systems, for the purpose of processing queries quickly and managing massive amounts of data, parallel database systems use parallel computing. To improve database performance and enable concurrent data access, parallelization techniques like query parallelism and data partitioning are used. Advantages of parallel computing. Cost efficiency. Parallel computing can help you save money by utilizing commodity hardware with multiple processors or cores rather than expensive specialized hardware. This makes parallel computing more accessible and cost-effective for a variety of applications. Fault tolerance. Systems for parallel computing can frequently be built to be fault-tolerant. The system can continue to function and be reliable even if a processor or core fails because it can continue to be computed on the other processors. Resource efficiency. Parallel computing utilizes resources more effectively by dividing the workload among several processors or cores. Parallel computing can maximize resource utilization and minimize idle time instead of relying solely on a single processor, which may remain underutilized for some tasks. Solving large-scale problems. Large-scale problems that cannot be effectively handled on a single machine are best solved using parallel computing. It makes it possible to divide the issue into smaller chunks, distribute those chunks across several processors, and then combine the results to find a solution. Scalability. By adding more processors or cores, parallel computing systems can increase their computational power. This scalability makes it possible to handle bigger and more complex problems successfully. Parallel computing can offer the resources required to effectively address the problem as its size grows. Disadvantages of parallel computing. Increased memory requirements. The replication of data across several processors, which occurs frequently in parallel computing, can lead to higher memory requirements. The amount of memory required by large-scale parallel systems to store and manage replicated data may have an impact on the cost and resource usage. Debugging and testing. Debugging parallel programs can be more difficult than debugging sequential ones. Race conditions, deadlocks, and improper synchronization problems can be difficult and time-consuming to identify and fix. It is also more difficult to thoroughly test parallel programs to ensure reliability and accuracy. Complexity. Programming parallel systems, as well as developing parallel algorithms, can be much more difficult than sequential programming. Data dependencies, load balancing, synchronization, and communication between processors must all be carefully taken into account when using parallel algorithms. And there you have it, an introduction to the captivating world of parallel computing. This technology is shaping the future of computation, driving innovation in various fields. If you found this video informative, don't forget to give it a thumbs up and share it with your fellow tech enthusiasts. For more exciting explorations into the tech universe, subscribe to our channel. If you have any questions or topics you'd like us to cover in future videos, drop a comment below. Thanks for joining us today, and until next time, happy computing.